Good morning. My name is Omar, and we're here at Physics News Network. Today's top story is about a group of scientists attempting to change acceleration by increasing mass in a cart and a pulley system. Would physics predictions hold true, or would experimental reality tell a different story? Let's go live to our field reporter, Mark. Take it over, Mark.
Thanks, Omar. I'm here at the physics laboratory where all this experiment took place. And right here, this is what the scientists are using. They're using this air blower to put in some air onto this cart pulley system right here. And as you can see, this cart pulley system is going to weigh about 5 grams. And they have a hanging mass on this little pulley and string that's about 20 grams. I believe they said that their first experiment was 15 grams and they wanted to increase it by 30%. So now we're using 20% is what they said. So what you're going to do here, from what they told me, the scientists, is that you're going to bring this card in and it's going to bring out... Okay, so what you want to do here is you want to bring this cart and it's going to push and it's going to bring this little graph right here and it's going to show the velocity over time graph. And this is all made by using this capstone Pasco system with the computer. And right now we're going to talk to one of the scientists and she's going to explain all the results that she got with this experiment. I'm here with professional physics scientist Tesla and she's going to go over the results of the old and the new experiment. Hello Tesla, how are you doing today?
I'm doing good. How are you?
Doing good. Can you let us know what the old experiment's acceleration was?
So the old experiment's acceleration was negative 0.373
Was it meters?
meters per second squared, yes.
Oh, okay. Cool. And then what about the new experiment? What did you get for the acceleration there?
We got negative 0.93 meters per second squared.
You heard it here first, fellas.
That was awesome, Mark. Thank you, Tesla, as well. We're going to take a quick break, and now here's a word from our sponsor.
Watch these 3 trucks race, but look closely. They're not all carrying the same load. Even if the engines are producing similar force, the results aren't the same. This is Newton's second law in action. Acceleration equals force divided by mass. When a truck tows more weight, its total mass increases, and with greater mass, the same engine force produces less acceleration. That's why the lighter truck pulls ahead. It has less mass resisting the change in motion.
And we're back. Man, that truck has some real power to it. Kind of looks similar to the problems that we're looking at in our physics lab. Now to go back to Mark to take a look at our final results of our experiment. Take it away, Mark.
Thanks, Omar. We're back at the lab and we've seen the setup. We've seen the experiment, but now we want to know what the results actually tell us. So I'm here with the lead data scientist, Alejandra, and she's going to walk us through what exactly happened with the experiment. Hello, Alejandra. How are you doing today?
I'm doing good, Mark. Thank you for asking. How are you doing?
I'm doing good. Can you let us know what the experiment and the results actually tell us?
Of course. So when we increase the hanging mass from 15 grams to 20 grams, we observe a noticeable change in acceleration. The original experimental acceleration was negative 0.373 meters per second square, while the new experiment measure is negative 0.93 meters per second square. When we compared those values, we calculated a 149.3% difference, showing that increasing the mass significantly changed how the system moved.
So the system definitely changed, but theory predicted something much larger, right?
Exactly. Using the Newton's second law, the theoretical model predicted a new acceleration of 7.84 meters per second square compared to the original theoretical acceleration of 0.70 meters per second square. This produced a 1,020% theoretical difference. In other words, theory expected a dramatic increase in acceleration.
But the experiment didn't match the prediction perfectly. How did you measure how accurate the experiment actually was?
Okay, so we use something called percent error, which compares theoretical predictions to experimental results. In the original experiment, the percentage error was 47.1%. After modifying the masses, the percent error increased to 88.1%. This tells us the new experiment agreed less closely with theoretical expectations than the original mass.
So you heard it here first, guys. So we got all the results from our lead scientists, Tesla and Alejandra, and now we're throwing it back to you, Omar. Thanks.
And that's all for today, folks. Thank you guys for watching. We'll see you guys next time on the Physics News Network.
One of the most important conceptual takeaways from this lab was fully understanding the difference between percent change and error, because even though they sound similar, they actually serve very different purposes in scientific analysis. Kind of like how extra credit and extra homework sound very similar, but again, feel very different emotionally. Percent change measures how much a quantity increases or decreases relative to its original value. It focuses purely on the amount of change between two values and helps us describe how significantly something has shifted. In our experiment, percent change, or percent difference, was used when comparing our old theoretical acceleration to our new theoretical acceleration after modifying one of the masses. This allowed us to quantify how much our intentional adjustment affected the system. It didn't tell us whether we were correct or incorrect. It simply told us how different the two accelerations were in relative terms. It's basically the statistic that says, wow, things changed, without assigning blame. Percent error, on the other hand, serves a completely different role. Instead of comparing two design choices, it compares our experimental measurement to a theoretical or accepted value. Its purpose is to measure accuracy, and unlike group projects, this one clearly tells you how close you were to doing it right. Percent error tells us how close our real-world data came to what physics predicts should happen. In this case, we used percent error to evaluate how well our measured acceleration matched theoretical acceleration calculated using the mass values and gravitational acceleration. So while percent change helps us understand the impact of modifying the system, percent error helps us understand the quality and reliability of our measurement processes. Basically, the difference between we changed something and we did it correctly. Another key difference is that percent change can either positive or negative, depending on whether the value increased or decreased, which gives information about direction. Percent error, however, is typically expressed as an absolute value, because accuracy is about magnitude of deviation, not direction. In scientific experiments, we care about how far off we are, not whether we overshoot or undershoot. Physics isn't judging our feelings, just our numbers. The distinction is subtle but important because it shows that percent error is focused on precision and experimental uncertainty, while percent change is focused on comparison and variation. This lab really helped clarify that percent change answers the question, how much did the system change when we modified it? Whereas percent errors answer the question, how well did our experiment match theory? Understanding that difference prevents confusion when analyzing data. If we mix them up, we might incorrectly interpret a large percent change as meaning our experiment was inaccurate, when in reality it simply means we made a significant adjustment to the masses. Similarly, a small percent change does not automatically mean our experiment was accurate. That judgment comes from percent error. In other words, one tells us how dramatic the change was, and the other tells us whether physics is giving us a polite nod of approval. Overall, this experiment strengthened our understanding of how theoretical physics connects to real-world measurement, especially through the use of percentage error and percent difference as analytical tools. By intentionally modifying only one mass in our system, we were able to directly observe how acceleration depends on the relationship between force and total mass. Increasing the hanging mass increased the net force pulling the system, while increasing the glide mass increased inertia and resisted acceleration. Seeing this relationship play out in actual data made our equation for theoretical acceleration feel less abstract and more physically meaningful, like the formula finally stepped out of the textbook and said, "See, I told you." Beyond just calculating acceleration, this lab emphasized the importance of interpreting data critically. When we compared our old data and new theoretical accelerations using percent difference, we were analyzing the design of our experiment. we essentially evaluating how significant our modification was. Then, when we calculated percent error for both trials, we shifted our focus from design to accuracy. This allowed us to reflect on sources of experimental uncertainty such as friction in the track, slight misalignments, limitations to the motion sensor, reaction time when starting the system, and rounding errors in mass measurements. Even small imperfections can influence acceleration measurements, because in physics, even tiny mistakes can have big opinions. Comparing the percent errors for both experiments also encouraged us to think about consistency. Ideally, if our setup and measurement technique were reliable, the percent errors should be relatively similar. If one trial showed us a much larger percent error, that suggests additional variables may have affected that run. This type of reflection is essential in experimental science because it helps identify the systematic errors and areas for improvement rather than simply accepting results at face value. Science doesn't just ask what happened, it also asks why did that happen, and can we fix it before the next lab? Additionally, comparing the percent differences between our experimental accelerations and the percent differences between our theoretical accelerations helped us evaluate how well our real-world models the ideal system described by equations. If these values were close, it suggests that our experimental setup successfully represented the theoretical assumptions. If they were not close, it highlights the impact of non-ideal conditions like friction and air resistance. One major lesson from this lab is why percentage-based comparisons are more meaningful than raw numerical differences. A difference of 0.2 meters per second squared may sound small, but depending on the original acceleration, that could represent a large proportional change. Percentage allows us to normalize our comparisons and evaluate significance in context. This makes our analysis more scientific and less subjective. In conclusion, this lab was not just about calculating acceleration, it was also about developing a deeper understanding of how experimental physics works. We learned how modifying variables affects motion, how to predict outcomes mathematically, how to measure results carefully, and how to evaluate accuracy using percent error. We also learned how percent change and percent difference help describe variation, while percent error measures reliability. By combining mathematical theory with hands-on experimentation and critical analysis, we gained a clearer understanding of both the physical principles of acceleration and its importance of precision scientific measurement, and maybe even earned physics quiet respect along the way.